Alright everyone, today we're going to talk about lesson 1-4. We're going to talk about continuity and one-sided limits. The first thing we're going to talk about is the definition of continuity. And within that, first we're going to talk about continuity at a point. And we talk about continuity at a point if a function f is continuous at some x value we'll call c when these three conditions are met. And the first condition is that f of c is defined. So there's a value. When we put c in to the function, we can get a y value back. The other condition, or our second one, is that the limit of f of x as x goes to c, it has to exist. And our third and final condition for continuity at a point is that the limit of f of x as x goes to c is equal to f of c. Sorry, I wrote that wrong. Let me fix that. So not only are we going to talk about continuity at a point, we're going to talk about continuity on an open interval. So here we would say a function is continuous on an open interval from a to b when the function is continuous at each point in the interval, and a function that is continuous on the entire real number line, meaning from negative infinity to positive infinity, is called everywhere continuous. We also say if we don't have continuity, if a function's not continuous, we call that discontinuity. And there are two different types of discontinuity. We've got removable discontinuity and all that means is that the function can be made continuous at c by defining or redefining f of c. The other type of discontinuity we have is non-removable. And what non-removable discontinuity means is when we cannot make a function continuous at c by redefining f of c. In our first example, example 1, we're looking at continuity of a function. We're going to look at the function and discuss whether it's continuous or not. So our first function we're going to look at, we'll call part A, is f of x is equal to 1 over x. How we're going to determine if this function is continuous or not is we're going to look at the domain of the function. And in this case, the domain of our function f is all non-zero real numbers. Because if we used 0, we would have a denominator of 0, and we can't divide by 0. We'd have an undefined portion. So what we can conclude from this is that f is continuous at every x value in its domain. However, at x equals 0, f has what we're going to call non-removable discontinuity. In other words, what we say is there's no way we can say f of 0 exists. So the function is continuous at all points except for x equals 0. Our second function we're going to look at, we'll call this function b, is going to be g of x is equal to x squared minus 1 over x minus 1. Here we say, when we're looking at the domain of g is going to be all real numbers, except we know that x cannot equal 1. Because if x was 1, we'd have a denominator of 0, and we can't divide by 0. G is continuous at every x value in its domain however, unlike our previous example, this one is going to have removable discontinuity. So at x equal 1, g has removable discontinuity. Because in the last lesson we talked about how we could factor our numerator, and if we want to try that, x squared minus 1 does factor to x plus 1 times x minus 1, and that's all over x minus 1, and we can cancel out the x minus 1's. So we could redefine the function to be just x plus 1. That is how we can say g of x has the removable discontinuity. We're also going to look at a third and a fourth function. So our third function we're going to check out, we're going to call it h of x. And this is going to be a piecewise function. So we're going to have x plus 1, and that will work for all values of x that are less than or equal to 0. And then we have x squared plus 1. where that works when all x values are greater than 0. How we talk about the continuity of this function, we still look at the domain, and the domain of h is actually all real numbers. There are no values we cannot use for x to get an h back. So what this means is the function h is continuous on the interval -infinity to 0 and to infinity. Because if we were to find the limit as x approaches 0, we could find that it would be 1. And the final function I want us to look at to determine continuity is going to be y equals the sine of x. And how we determine this continuity or discontinuity, we still look at the domain. So the domain of y is actually going to be all real numbers again. There's not a value of x that we can't plug in. We can utilize our unit circle to find values of x. We can always go different rotations of 360 or even -360. So from that, we can conclude that the function is continuous for the entire domain. So just to kind of recap continuity versus discontinuity, a function will be continuous if all real numbers work in it. If the domain can be all real numbers and there's no conditions to it, no exclusions, we have a continuous function. If there is a value or a set of values that we cannot use, like in example 1a and 1b, then we have discontinuity. If we can alter and redefine the function like we did in 1b, we call that removable discontinuity. If we can't, like in 1a, we call that non-removable. So now let's talk about one-sided limits and continuity on a closed interval. So up to now, what we've been doing with limits we've been looking at limits that are approaching from both sides of C, from the left and the right. We're now going to start looking at limits that only approach from one side. So if we have, say, the limit of f of x as x approaches C, but then they add this little plus sign that kind of looks like an exponent with the C, and it equals L. This means we're looking at limits from the right. If we were looking at the graph, we would only look at the right side of C. And then let's say we were looking at a left-bounded limit. That is going to look different than a right-bounded limit. For example, a left-bounded limit is going to look similar. We're going to say the limit of f of x as x approaches C. But instead of having a little plus sign above C, we're going to have a little minus sign. And we're going to still say that equals L. These are limits from the left. So if we're looking at the graph of the function, we're just looking at any points that are to the left of C. This will come in handy specifically when we're looking at taking limits of functions that have radicals. So a general thing we can write is that the limit of the nth root of x, as let's say x approaches 0 from the right, that's going to equal 0 when we have n as an even number. So now let's talk about example 2, where we are going to find the limit of our function, and we're going to have this function be f of x equals the square root of 4 minus x squared as x approaches -2 from the right. So if we were using the notation we just looked at, we would write this as the limit of the square root of 4 minus x squared as x approaches -2, and since it's from the right, we'd put a little plus sign. We need to figure out what that equals, and there's a couple different ways we can do this. If we know the function is continuous, we can figure out the limit through direct substitution. If we're not sure if the function is continuous, then we can use a graphing calculator or make a table of values and find the limit as we approach -2 from the right, which means we would take values that are larger than -2 to test our limit. I want to draw the graph that would go to this function. So here's a rough sketch of what you would see on a graphing calculator if you did put the square root of 4 minus x squared into it. If we are wanting to look at the limit as x approaches -2 from the right, we are going to follow our function until we see what is the value of f of x at -2 from the right side. And what we see is that this limit gets closer and closer to y equals 0. So the limit is going to equal 0. So let's quick take a look at what we're going to call the greatest integer function, where it's written as f of x is equal to an interesting bracket that has an extra line in it, x, and then we close that bracket. What that means is that we are looking for the greatest integer value, which we'll call n, such that n is less than or equal to x. So let's quick look at example 3, and we're going to find the limit of this greatest integer function as x approaches 0 from the left. I'm going to quick put the graph of the greatest integer up. What we notice about this function as we get closer and closer to 0 from the left is that y gets closer and closer to -1. So the limit is going to equal -1. Tune in for part 2 of our 1-4 lesson.